Imagine a building so powerful it can produce electricity for millions of homes day and night without stopping, but hidden inside its massive walls is enough energy to change an entire city or destroy it in seconds. Just hearing the words nuclear power plant makes many people think of explosions, radiation, Chernobyl, Fukushima disaster, but here's the surprising truth: modern nuclear power plants almost never explode, even though inside the reactor, atoms are constantly splitting apart, releasing an unbelievable amount of energy. Temperatures reach hundreds of degrees. The reactor core contains enough fuel to power entire countries, so why doesn't it explode like a bomb? What stops the reactor from melting down? What happens if the power suddenly goes out, or a massive earthquake strikes, or a tsunami hits the plant? Could everything go wrong, or is there a hidden system working silently every second to prevent disaster? The answer is one of the greatest engineering achievements ever created, a machine protected by layer after layer after layer of safety. Today, we are going inside a nuclear power plant to discover how nuclear reactors really work, why they don't explode, and the incredible engineering systems designed to keep millions of people safe. This is the engineering behind nuclear power. To understand why a nuclear power plant doesn't explode, we first need to understand what's happening inside the reactor. At its heart are small fuel rods, each one filled with tiny uranium pellets. These pellets may look harmless, but inside them a powerful reaction is taking place. Atoms of uranium are constantly splitting apart. This process is called nuclear fission. When one atom splits, it releases a huge amount of heat. It also releases tiny particles called neutrons. These neutrons strike other uranium atoms, causing them to split as well, creating a chain reaction. At first, this sounds extremely dangerous. If atoms keep splitting, won't the reaction continue forever? The answer is no, because engineers never allow the reaction to run out of control. Instead, the reactor is carefully balanced every second using special control rods. These rods are made from materials that absorb neutrons. When inserted deeper into the reactor, they capture more neutrons, slowing the chain reaction. If pulled upward, the reaction speeds up slightly, not because the reactor is becoming dangerous, but because the power output must match the electricity demand. Thousands of sensors monitor everything: temperature, pressure, radiation, coolant flow every second. Powerful computers automatically adjust the system, keeping the nuclear reaction perfectly stable, not too fast, not too slow, exactly as engineers designed. Because inside a nuclear reactor, control is everything. This is the biggest misunderstanding about nuclear power. Many people believe a nuclear reactor could explode like a nuclear bomb, but that's physically impossible. Here's why: a nuclear weapon uses highly enriched uranium designed to release almost all of its energy in a fraction of a second. Everything happens instantly, creating a massive explosion. A nuclear reactor is completely different. Its fuel contains much lower levels of enriched uranium, far below what is needed for a bomb. Even if every safety system stopped working, the fuel itself cannot produce a nuclear explosion. It's simply not designed that way. So what actually can happen? The real danger isn't an explosion, it's overheating. If the reactor isn't cooled, the fuel rods become hotter and hotter. Eventually, they could begin to melt. This is called a nuclear meltdown. Notice the difference: a meltdown is not a nuclear bomb, it's an engineering failure, not a nuclear explosion. And that's exactly why modern reactors focus so much on cooling, because as long as the reactor core remains cool, the system remains safe. This is why every nuclear plant has multiple independent cooling systems. Even if one system fails, another immediately takes over, and if something goes seriously wrong, the reactor can shut itself down within seconds, preventing the chain reaction from continuing. Modern nuclear plants are built with one goal above everything else: keep the reactor under control every second, every minute, every day. Now imagine the impossible: the electricity suddenly fails, every light goes out, the reactor automatically shuts down, problem solved, not quite, because even after the chain reaction stops, the reactor core is still extremely hot. In fact, it continues producing heat for hours and even days. This remaining heat is called decay heat. If it's not removed, the fuel rods can overheat. Eventually, they could begin to melt. So how do engineers prevent this? The answer is cooling. Massive pumps continuously circulate cool water through the reactor. The water absorbs the intense heat, then carries it away to giant heat exchangers and cooling towers, keeping the reactor core at a safe operating temperature. But what if the pumps lose power too? Modern nuclear plants already have a backup plan. Within seconds, emergency diesel generators start automatically providing electricity to the cooling pumps. If those also fail, another layer takes over. Large battery systems continue powering critical equipment. Some modern reactors go even further. They use passive cooling systems. These systems don't need electricity. They rely on gravity, natural water flow, and simple laws of physics to remove heat without any moving parts. Finally, if sensors detect a serious problem, the reactor performs an emergency shutdown known as SCRAM. Control rods drop instantly into the reactor core, absorbing neutrons, stopping the nuclear chain reaction. Within seconds from that moment, the only mission is cooling. Because engineers know stopping the reaction is only a first step. Keeping the reactor cool is what truly keeps everyone safe. Even if the reactor is operating perfectly, there is still one important question: how is radiation kept inside? The answer is simple: it never depends on just one barrier. Modern nuclear plants use multiple layers of protection. The first layer is the fuel itself. The radioactive material remains sealed inside strong ceramic pellets. These pellets are placed inside heavy metal tubes called fuel rods. This creates another protective barrier around them. Flows the reactor vessel, a gigantic steel container with walls more than 20 centimeters thick, built to withstand extreme heat and pressure. But engineers didn't stop there. The entire reactor is surrounded by an enormous containment building. This building is made from reinforced concrete and thick steel. Some walls are more than 1 meter thick, strong enough to resist powerful explosions, extreme weather, and in many plants, even the impact of a large aircraft. Inside a containment building, powerful filtration systems continuously monitor the air, detecting even the smallest signs of radiation. If anything unexpected happens, automatic safety systems immediately isolate the reactor, preventing radioactive material from escaping. Every pipe, every valve, every door is designed with safety as the first priority. That's why modern nuclear plants don't rely on a single safety system. They rely on many, each one ready to protect the next. It's called defense in depth. One layer fails, another takes over, then another and another, until the reactor and everyone around it remains safe. When people hear the words nuclear power, two names almost always come to mind: Chernobyl and Fukushima. Both accidents changed the world forever, but they also changed nuclear engineering. After Chernobyl, engineers discovered how dangerous poor reactor design and human mistakes could become. Modern reactors were redesigned with completely different safety systems, automatic shutdowns, stronger containment buildings, multiple backup systems, and far better operator training. Then, in 2011, a massive earthquake struck Japan. Moments later, a devastating tsunami destroyed electrical systems at the Fukushima plant. Without electricity, cooling systems stopped working. The reactor cores began to overheat, although the reactors had already shut down. This accident taught engineers another important lesson: cooling must continue even after the reactor stops. Today, modern nuclear plants include even more emergency systems, extra backup generators, higher flood barriers, waterproof electrical equipment, passive cooling systems that work without electricity. Some reactors can safely remove heat for days without human intervention. Others are designed so that Even if every operator walked away, the reactor would automatically move toward a safer condition. Every major accident has led to new rules, better technology, and stronger safety standards. Modern nuclear plants are not the same machines built decades ago. They are the result of generations of engineering improvements, each lesson making the next reactor safer than the last. And that is exactly why modern nuclear power looks very different from the past. So, how do nuclear power plants avoid exploding? The answer isn't luck. It's engineering. Every second the nuclear reaction is carefully controlled. Control rods regulate the reactor core. Powerful cooling systems remove enormous amounts of heat. Emergency shutdown systems stand ready to stop the reaction within seconds. Thick steel vessels and massive concrete containment buildings keep radiation safely inside. Multiple backup systems wait silently, prepared for the unexpected. Even if one layer fails, another immediately takes over. This is why modern nuclear plants are designed around one principle: safety before everything. Of course, no technology is completely risk-free, but today's reactors are the result of decades of research, lessons learned, and continuous engineering improvements. The next time you see a nuclear power plant, remember this: you're not looking at a giant bomb, you're looking at one of the most carefully engineered machines ever built. A system designed to produce massive amounts of clean electricity while protecting the people working inside and the millions living around it. That is the incredible engineering behind modern nuclear power. If you enjoyed this documentary, don't forget to like, share, and subscribe to RailForge, because here we uncover the incredible engineering behind mega structures, modern technology, and the machines that power our world. Thanks for watching, and we'll see you in the next documentary.